Now see the 13th topic now. Static indeterminacy. Kinematic indeterminacy and stability of structures. In the moment distribution method, slope deflection method, I told you if dk is less, the slope deflection method is best suited. Quickly you can get the unknowns. If dk is 1, then only one joint equilibrium equation is required to analyze the problem. Then in compatibility methods, whatever you have learned in strength of materials, we told you ds is equal to 1. So, only one additional compatibility condition was required to analyze all strength of materials problems that we have already studied. In the trusses I have given you indeterminate trusses, I gave you external indeterminacy, deals with only support reactions, DSC is R minus S. Then we have given one more problem which deals with the internal indeterminacy. How many members are there in excess of equilibrium equations? So, at two hinged arches also we have seen it is indeterminate to 1 degree. Now we will see all the things: static indeterminacy, kinematic indeterminacy, stability of beams, trusses, frames. At one place we keep them so that in the exam any question comes, quickly you can refer to this, recollect these ideas and answer the questions in our stipulated 30 seconds time. Any question given on static indeterminacy, kinematic indeterminacy and stability of structures will not take more than 30 seconds time for us. Okay. So, first we will take up the static indeterminacy. Static indeterminacy ds. It consists of two parts: external indeterminacy plus internal indeterminacy. Okay. So, we split into two parts. This is external indeterminacy. We call it as ds external. This is internal indeterminacy. We call it as DSI. Sum of external indeterminacy and internal indeterminacy is the total static indeterminacy. Okay. How many members are there in excess of equilibrium equations and how many support reactions are there in excess of equilibrium equations? Put together is the total static indeterminacy. Static indeterminacy means, again, static means from the equations of statics point of view. Indeterminacy means you cannot determine. Here static means from the equations of statics. From the equations of statics consideration, it is indeterminate. Equations of statics means equations of equilibrium, sigma x0, sigma y0, sigma m0. Okay. So, from the equations of statics consideration, they are indeterminate structures. Then such indeterminacy is external plus internal. External deals with support reactions only. It deals with support reactions only. Internal indeterminacy, it deals with internal member forces. Internal member forces means axial force, shear force and bending moment only. It deals with internal member forces only. Then what is external indeterminacy means? It is the number of reactions in excess of equilibrium equations. In excess of equilibrium equations, external equilibrium equations. Then it is the total number of member forces in excess of internal equilibrium equations. Total number of member forces in excess of equilibrium equations. So, this is how let us see how to calculate external indeterminacy first for beams, trusses, frames. Then we will calculate internal indeterminacy for beams, trusses, frames. Then without calculating separately DSE, DSI separately calculating and adding them and wasting the time, total at once we calculate. Okay. Let us see one by one concept. Now first we will take up the external indeterminacy. I remove this part. This is like introduction. First you will see external indeterminacy, internal, then total. First one is external indeterminacy. DSE is nothing but R minus S. R I have given you already, total number of unknown reactions, total number of equilibrium equations available. R minus S will give you the external indeterminacy. Now, let us see how to calculate for the fixed beams. What are the issues involved in this one? Assume that we have a fixed beam subjected to some general loading. General loading means can be vertical loading, inclined loading and also moments also. Whatever load that we want, we can apply A, B. This is most general case. Number of unknowns. In this case, fixed support as we have known, it will give you three reactions VA, HA and MA. Here VB, HB and MB. So, unknown support reactions are 6 VA, HA, MA, VB, HB, MB. Then equations of equilibrium available. Equations of equilibrium available. Available are three. What are they? Sigma x0, sigma y0, sigma m0. So, DSE you will get R minus S, that means 6 minus 3. You will get 3 degrees. That means fixed beams subjected to general loading are statically indeterminate to 3 degrees. Fixed beams subjected to general loading. General loading means which includes inclined loading also. fixed beam subjected to general loading are statically indeterminate to 3 degrees. 3 degrees they are indeterminate. This is what we have studied. Next, if I take second case, a fixed beam subjected to vertical loading, only vertical loading is there, say W1, W2. No height is the same line. Such cases, the horizontal reaction exerted will be almost equal to 0. HB, HA 0 because there is no horizontal action, no horizontal reaction. Then what are left out is now VA, MA. This point let us say A, this point say B. This is VB, MB. Now, by writing sigma x is equal to 0, this is now become useless and HA and HB automatically became 0 because there are no actions. So, one equilibrium equation is gone, two unknown reactions have now become known quantities. Now, R stands for total number of unknown reactions. Now, unknown reactions are only 4, not 6. What are they? VA, MA, VB, MB. Okay. S means total number of equations of equilibrium available. Equations of equilibrium available are now only 2, sigma y0, sigma m0, because sigma x0 is already gone. Now you will find that dSE is equal to R minus S, 4 minus 2, 2 degrees you will get. So what is your conclusion? Fixed beams subjected to vertical loading this here is general loading, it is vertical loading or indeterminate to 2 degrees. Okay. Supposing that if axial loading is there, how it should be done? You have a fixed beam A, B subjected to axial loading, some P let us say. Such problems you have done in your strength of materials. First chapter, simple stresses and strains chapter, these problems you have done. Axial rigidity AE, 2AE like that, same AE, AE. Then you have used compatibility condition. Okay. Now, one compatibility condition only you have used in strength of materials. That means it is indeterminate to 1 degree only. Why it is only 1 degree? Vertical load is not there. So, vertical reaction is 0. So, VA is 0, VB is 0. No transverse load is there, it is not bending. So, we know for sure that MA is equal to 0. MB is also 0. Now, you see sigma y0 is useless and VA and VB we could say that it is 0. Sigma M is 0 is also useless. We could say that MA is equal to MB is equal to 0. For this particular case, fixed beam subjected to axial loading, 2 equations of equilibrium are useless. 4 unknowns now became known quantities. So, how many unknown reactions left out? Only 2, HA, HB. Equations of equilibrium left out only 1, sigma x is equal to 0. Because sigma y 0 gone, sigma m is equal to 0 is also exhausted. So, static indeterminacy you will get r minus s 2 minus 1, you will get 1 degree. So, what is your conclusion from this? Fixed beams subjected to axial loading are statically indeterminate to 1 degree axial loading. So, from this what you understand is any structure depending on the type of loading, static indeterminacy can change. If at all in the examination loading is not given, then that means the structure can be subjected to any type of loading, general loading. So, static indeterminacy you have to answer 3. So, because no loading is given, you have to assume general loading. But if they give you the loading like this, for this loading only what is the static indeterminacy you have to calculate. If they specifically mention the diagram and loading also, then for that loading it is only 2 degrees. For this loading it is only 1 degree. Fixed beam subjected to axial loading, strength of materials you have calculated, the reactions H and HB. Because it is statically indeterminate to 1 degree, you have used one compatibility condition. What is that? Elongation in AC is equal to contraction in CB. That is one compatibility condition. Equilibrium equation sigma x 0. So, one compatibility condition extra we required because 2 unknowns are there, one equation of equilibrium. This we have done in your strength of materials 1 at the beginning of strength of materials. Then in strength of materials 2, where you have studied about the fixed beams, deflections, etc., this you have taken in SM2, strength of materials 2. So, there you have dealt with only one problem, fixed beams are statically indeterminate to 2 degrees. That means you require 2 compatibility conditions. What are the conditions? Sir might have told you, even I have explained to you, the 2 compatibility conditions are the angle between the 2 tangents drawn at A and B is 0. So, theta is equal to 0, A by EI is equal to 0. Second compatibility condition is if you draw the deflection profile, the deviation BB dash is also 0. So, AX bar by EI is also 0. So, that is the second compatibility condition. So, solve the 2 compatibility conditions, you will get the MA, MB. Once MA, MB are known, VA, VB you can find from equations of equilibrium. 2 equations of equilibrium, 2 unknowns we can find. In our entire strength of materials, static indeterminacy 2 problems, only these fixed beams we have solved, if you tell you vaguely remember. Then fixed beams subjected to general loading, this you will study in matrix methods, where you write the general, even axial forces in the members also we will try to find by writing the stiffness matrix or flexibility matrix. That we will see in the later stages, how we should develop the stiffness matrix and flexibility matrix for fixed beams subjected to general loading. Okay. So, this is about the general information. It can be 3, 2, 1 depending on the type of loading. Okay. Next. Now, this I remove. Now, see here you will write a note. If nothing is mentioned in the problem, nothing is mentioned in the problem means whether loading, shall we take general loading or vertical loading or axial loading, which one to take? If nothing is mentioned, then you have to take general loading only. Then assume general loading and find DSE. Okay. Now let us see how numericals can come in the exam. Find DSE. This point, let us say A, B, C, D, or let us say we give either this way they can give, or they can give you a roller, because reactions will be same in such cases. Okay, like this. See here, nothing is mentioned in the problem, type of loading is not given. So here three reactions, HA, VA, MA. Here roller, so only VB. There is MB also, but that is internal. Roller support can give only one external reaction. Your external indeterminacy deals with the support reactions only. Internal moments MBA and MBC also will be there. But if you write MBA plus MBC is equal to 0, that is internal joint equilibrium equation. Okay, nothing to do with our external equilibrium equation. VB, VC, then this is VD, HD and MD. Now you see 3, 4, 5 plus 3, 8. So unknown reactions are 8. Equations of equilibrium are 3. Sigma x0, sigma y0, sigma m0. So you will get DSE, external indeterminacy is R minus S, 8 minus 3. You have to write answer as 5 degrees. So one of the options will be 5 degrees. If 5 is not there, then you may have to assume vertical loading. Same question, let us see, find DSE. Some load they give you P, let us say, then A, B, C, D. If same problem but load is given, then for this loading only what is the static external indeterminacy you have to calculate. For this loading HA 0, HD is also 0, then you have VA, then you have MA, this is VB, VC, this is VD and this is MD, this is HD. Now you see sigma x is equal to 0 is gone, HA, HD is also gone. How many unknown reactions left here? 2, 3, 4, 5 and 6. Unknown reactions are only 6. Equations of equilibrium available are only 2, sigma y0, sigma m0. That's all. Here it is VA, MA, VB, VC, VD, MD, like this. So only 6. So static external indeterminacy is R minus S, 6 minus 2 is equal to 4 degrees. Now two possibilities. Loading is not given also, let us say, but 5 is option itself is not there, then 4 is there. First type of problem is they give you no loading, one of the options is 5, then 5 you have to answer. Second type of asking the same question is this one. Loading is given, then 5 will be there, 4 will be there, then 4 you have to answer. 4 degrees because loading is given. Now third possibility is, this is the problem, 5 is not there. 4, 3, 2, 1 options they have given for this case, let us say. Then first you have to search for 5. If 5 is not there, then you can answer maybe he is taking that vertical loading is there, then 4 he must be thinking is the answer. Then you can answer 4. For this case you can answer 4 if 5 is absent. Otherwise 5 only have to answer. I think I made it clear. For the given type of loading, if nothing is mentioned, assume general loading. Find say 5. If 5 option is not there, only 4 onwards it started. 6, 4, 3, 2 like that. Then you must answer 4 because maybe he was thinking vertical loading only, then 4 is there like that. Okay. Options will tell us how we should think about the problem. Now, let us see how to deal with the trusses. Case 2. For trusses. Case 1 is for beams. What I gave earlier is beams. Now case 2 is for trusses. Find this also same as beams only. Some truss is given say like this. Generally continuous trusses will not be there. For the sake of completeness I have given you like this. This point let us say BC. There are two reactions VA, HA, VB, VC. So unknown reactions are 4 VA, HA, VB, VC. Equations of equilibrium available are 3 sigma x0, sigma y0, sigma m0. So static external indeterminacy becomes r minus s, 4 minus 3, you will get 1 degree. So this is for the trusses. Next case 3. For frames. How we should manage for the frames. Now you see, assume that we have this, I think better I remove. Case 3 for frames. We want to find only the external indeterminacy. Assume that we have a frame like this. This is the fixed one. Different types of conditions can exist. Hinge support, a roller support. This is a guided roller support. Okay. This point let us say A, B, C, D. Now, in this case, there are three reactions: fixed support VA, HA and MA. Here it is VB, HB. Here VC. Here VD and MD. You see here MA, MD, both of them are couples only. They can offer, this guided roller support can offer a couple. That couple can be a vertical couple or a horizontal couple. Finally, movement curved arrow mark only we will show there. At the fixed support, as I told you, there is a footing here. When we show like this, there is a footing. Like this is there a footing below the soil. Now anti-clockwise couple means, how to develop the anti-clockwise couple? There will develop a force F here, F here. Perpendicular distance, let us say D. When the column is embedded into the footing, that footing must be capable of exerting a force like this and like this. F and F are the forces exerted by the footing on the column. Put together will form an anti-clockwise couple. Without that height, column footing thickness is there say. Without that having thickness, it cannot exert a moment. It cannot give the moment to the column. So there must, as I told you, if at all you show one curved arrow mark, it means that there must exist a couple like this. Without a couple, this type of curved arrow mark cannot exist. Now in this case, there is a horizontal couple. Now here, there is a guided roller support. Now what type of couple will develop? I think I have explained to you this point earlier, but otherwise we will draw the diagram also. Anti-clockwise couple means there is a steel plate. Here steel plate, column is welded so that 90-degree angle will be maintained. When I turn it like this, this cannot be lifted up. This cannot go down. It cannot be lifted up because there will exist a couple like this. So when I am applying a moment like this, anti-clockwise couple means when we show like this, there is a channel, as I told you earlier, there is a channel like this which will hold a rigid plate. There is a rigid plate, a channel will hold like this so that I cannot lift it up. If I lift it, channel flanges will press the rigid plate down. Other side also in the opposite direction. So it is guided. In the channel, this rigid plate can move forward, backward, but you cannot rotate. So moment reaction can exist there. So when we show anti-clockwise couple here, that means it is a vertical couple. This force F is exerted by the flange of the channel on the rigid plate. Here also there will exist a force F. The perpendicular distance is D. So F into D is this one, anti-clockwise couple. This type of couple can exist at the guided roller support. So that's why two reactions we have shown here. This is vertical couple. Here it is horizontal couple. Finally, whether it is a horizontal couple, whether it is vertical couple, horizontal couple, a curved arrow mark only we will show. Now, what is the static indeterminacy? Number of unknown reactions are how much? 3, 4, 5, 6, 7, 8. R is 8. VA, HA, MA, VB, HB, VC, VD, MD. Equations of equilibrium available are 3. Sigma x0, sigma y0, sigma m0. So external indeterminacy DSE is R minus S, 8 minus 3, in this case 5 degrees. Okay, now let us see this structural behavior of guided roller support. This free body diagram I think I have given earlier, but revision. Structural behavior of guided roller support. This is the column, let us say. This is the rigid plate, steel plate, rigidly welded. Now we have rollers. This is the base. I am applying, say, a clockwise movement. Let us say, then anti-clockwise movement will develop. See here, so many rollers must be there. It is similar to our table draw. If you see our table draws, sides channels will be there. Channels means C-type sections, they bolt them. So that draw can be moved forward, backward. That's all. When you lift it up, it will not be lifted because sides there are channels. And in the channel, when they to the draws, there are so many rollers attached to that. Those rollers roll forward, backward only like this. So when you lift it up, the table draw hits the upper flange. Push it down, it hits the lower flange. Push it left, it hits the web. So you cannot move sideward, you cannot move up and down, it can only be guided to move forward, backward. So that channel is like a guide. In the channel, the rollers are guided to move forward, backward only. So that's why it is called guided roller support. Okay. So now when I lift it up, it is supposed to go up. Who will stop? There is a flange, like this will hold it. This flange will press him down. Press the channel down. Press the rigid plate down. This is a steel rigid plate. To that it is welded. Now what will happen? When I try to lift it up, a force F will develop here. F is exerted by channel on plate. Here also same thing. There will be another force F. Actually the pressure distribution will be something different. When I try to lift it up here, pressure will be more, less, 0 here, opposite direction. The resultant downward force, that means pressure into area, here also pressure into area, somewhere in between it will act, but I have shown it diagrammatically like that, a simplified version. So F into D. So instead of showing F and D, generally we do not know the resultant pressure where it acts. Here also we don't know, but moment we can find whose resultant effect we can show. So the effect of these two forces, it's like a couple, a pair of equal oppositely directed non-collinear forces. It will form a couple. Only effect of that couple is moment. That value is MD. Instead of we don't know what is F, what is D, simply MD we will write. So like this. So that we have shown here MD. It can be anti-clockwise, clockwise, but that can offer that much resistance. So it will not permit the rigid plate to rotate. So moment reaction will develop at guided roller support. So in the frames, external indeterminacy is calculated like this. Difference between this and this is rollers are there, rigid plate. But instead of welding, you put one more triangular plate. To the triangular plate you pin it, say. There is a pin here, then it can rotate. So moment reaction also cannot develop. Such things simply we call it as roller support. And guided, when you use extra word, that it cannot be rotated also. Only moves forward, backward, that's all. If it can rotate, simply we say it is a roller. Okay. So that is the difference. Now let us see the second one, how to find internal indeterminacy. internal indeterminacy DSI. It is the number of internal member forces in excess of equilibrium equations. That is what I have given earlier. For beams, if you know the support reactions, you can find axial force, shear force, bending moment in any part of the beam, either it is simply supported or continuous beam. So, for beams there is no internal indeterminacy. Case 1. For beams, there is no internal indeterminacy for beams. Because if we know the support reactions, we can find axial force, shear force and bending moment. And bending moment at any section of the beam. At any section of the beam. Example is this one. Assume that we have a continuous beam. There is a roller here, roller. Okay. This point, let us say A, B, C, D, is subjected to so many forces. Assume that there is one inclined force W1, W2, angles let us say theta like this, some vertical force W3, so many forces are acting like this say. Now assume that you found the reactions already. Vd is known to us, Vc is also known to us, Vb is known to us, like this. So here Va, all the support reactions we know say. Then internally everything, axial force, shear force, bending moment you can find easily. Suppose at xx I want to find axial force, say axial force at xx. Axial force at xx. So what we have done, for in the strength of materials first chapter, sir might have told you, if you have a bar, A, B, C, D bar is there, subjected to forces F1, F2, F3 axial forces are there. At any section, what is the axial force in one particular member? What you have done? Stand on the section XX, look one side, either left side or right side. The unbalanced net force is the axial force, that's all. So, axial force in the member at XX is equal to stand at XX and look right. Don't want, you can look left also, our choice. So, this is acting right side. So, plus W1 cos theta minus W2 cos theta. So much tension, because arrow mark, when you stand here, arrow mark now is acting right side, say net arrow is right side, then it is tension. If net arrow is towards XX, compression. So, this is how you have done. Then after that, in the shear force and bending moment diagrams, you calculated shear force. What is the shear force at XX? Stand at XX and look right. What you have done? Then what is the shear force here? Section right side downward plus W3 minus Vd plus W2 sin theta minus Vc W1 sin theta. So that we know. Stand, look right. Summation of all vertical components of the forces. Here stand at XX, look right. If you look left and right, say, then this becomes sigma x is equal to 0. You will get net value 0. Here also, one side if you see, you will get axial force. Both side if you see, sigma x 0 it becomes. Shear force also, stand here, look one side, you will get shear force. Look both sides, then it becomes sigma y is equal to 0. Equilibrium equation, sum must be 0. Then bending moment at xx, what you have to do? Stand at xx and look right. One complete chapter we have learnt on this one. Stand here, look right. W3 into some 5 meters, Vd into 4 meters, W sin theta into 3 meters, like that. So this also we know. That means here also stand at xx, look one side, moments of all forces is called bending moment. Look both sides, moments of all forces, then it becomes equilibrium equation, sigma m is equal to 0. So that is the difference. Look both sides, equilibrium equation. Look only one side, axial force, shear force, bending moment we can get. Okay. So this is what we have learned. If you know the reactions, we can find axial force, shear force, bending moment in any part of the structure. That's why internal indeterminacy is 0 always. Okay. Next. Second one, case 2 for trusses. Now here we will write. For trusses internal indeterminacy I have given you. How many members are m is equal to 2j minus 3 is the condition. For any simple truss which is stable and determinate, condition is m is equal to 2j minus 3. I told you how we should derive that also. How many m is equal to 2j minus 3 means if the number of members are exactly equal to 2j minus 3, you will get a stable triangulated form. Then if you provide or if the number of members are less than 2j minus 3, then it becomes unstable. If you provide more members than 2j minus 3, it becomes indeterminate. We have to provide sometimes more number of members than 2j minus 3 to make the structure more stable. Such more members than 2j minus 3, I told you we call them as counter bracing. Okay, so that point here we are taking. Trusses means how many number of members are there in excess of 2j minus 3. That number we call it as internal indeterminacy for trusses. Okay, it is the number of members in excess of 2j minus 3. So DSI means m minus 2j minus 3. So more than 2j minus 3, how many are there you can get from this one? M means total number of members, J means total number of joints. Okay. Now, why 2J? 2J that we have given it number of equilibrium equations. This we have already, I explained to you that part. Example, find DSI. Supposing that we have a truss like this. Earlier we have calculated external indeterminacy, now we want to calculate internal indeterminacy. Same structure we have taken. Now you see, when a circle is not there means simply they are overlapping. Now how many members are there? 6 plus 5, 11. Number of members are 11. Then number of joints are 6. So internal indeterminacy means m minus 2j minus 3. 11 minus 2 into 6, 12 minus 3, 9. So 2 degrees. See here one triangle should be there, one into is there means there is one extra member is there. Here also one extra member is there which you cannot find using equations of equilibrium. Then in the 20 marks questions like that, then we have to use the compatibility conditions. That two compatibility conditions means beyond the scope. It will take more than 1 hour. So in the exam, in the mains, if at all they give you a 20 marks question, only one member extra will be there than 2j minus 3 to solve the question. Like this 2 means impossible for us to solve in our stipulated 6 to 7 minutes time. So 2 degrees. If DSI 2 degrees means there are two counter bracing members. Two counter bracing members. That is the meaning. Any one here, one counter bracing, any one of them can be counter bracing. We will use such counter bracing if the length of the diagonals are more. If they fail, another member will come. Depending on the type of loading, anyone can fail. If one fails, other will take care. Here also one fails, other will take care of the panel shear in the panel. Now let us see case 3 for frames. For frames. Now assume that we have a find DSI. For this case, external indeterminacy already we have found. Now we want to find only internal indeterminacy. Okay. So when you are finding internal indeterminacy, whether you take a truss or frame, support reactions are known to us, that is the assumption. Only internal indeterminacy we are finding. This is the case. While calculating DSI, it is assumed that support reactions are known to us because we don't want to deal with them. They are known to us. That means, supposing that you take, say, this is A, B, C, D. There are three reactions here: VA, HA, MA. These three values are known to us now. Here VB we know, HB we know, VC, VD, MD. So these all support reactions are known to us when you want to find only DSI. Now let us see. I want to find axial force, shear force and bending moment at 1, 1, let us say, in the column. How do you find what is the axial force at 1, 1? Stand there, look down. VA is the axial force. How will you find? By writing equilibrium equation. Having known that, you have some more equilibrium equations now. sigma y0 still I can use. For the equilibrium of the entire structure, you found the reactions fine. Now member forces if you want to find, axial force if I want at 1 1, stand at 1 1, look down. If I write sigma y0, VA is upward, so here it should be downward. That means here downward means it will be under at 1 1, axial force is downward on this member. That means bottom member if you take it, it is under compression. We can get from that. Downward means on this member compression. Sigma x0 if I write HA right side, here it is left side. So shear force at left side. Simply moment at 1 1 is MA. So I can find axial force, shear force, bending moment at 1 1 by using sigma x0, sigma y0, sigma m0 for this part alone. Now I want to find at 2 2, let us say. At 2 2 if I want to find, stand there, look one side. If it is like a cantilevering one, I can find axial force, shear force, bending moment. So when I see this side, this unnecessarily is extending. It is not looking like a cantilever. So make a cut here. Cut here, then only this part I can take free body diagram and find axial force, shear force, bending moment. What it means is this one. I am cutting it here. This is one member I am cutting it. This is the next one. There is a hinge here, extending like this. Something like this is extending. This point is B, this point is A. We know VA, HA already somehow you managed to find them. MA. At 1 1 now I could find. Now at 2 2 if I want to find, I must make a cut here and find the forces. Assume that at this point when I am cutting it here, this is H1, V1, some M1. Who will give these three forces? These three forces are exerted by this member on this member. If I know them somehow, then at 2 towards the axial force plus VA plus V1. But I must know that, but I don't know. Three equations of equilibrium are used to find here. Sigma y0 if I use, VA plus V1 is so much force here, compressive force. But V1 we don't know. That means you have to cut it. These many unknowns you cannot find using equations of equilibrium because they are already exhausted. Okay. So at this cut, three unknowns will be there. Now at 3 3, that means wherever you cut it, look one side, it should look like a cantilevering one. Cantilevering portions means not necessarily one member. There can be 10 members also, but those ends must be free ends. Then it is like a cantilever tree or cantilevering portion. So now this looks like a cantilever portion because it's broken. That means fixed support also looks like a cantilever because at the fixed support three reactions are there, VA, HA, MA. You pluck out the fixed support, put the three reactions. Now it looks like a cantilever with three forces, VA, HA and MA. A cantilever subjected to three forces. That's all. That means free body diagram you have drawn for a cantilever portion. Now here it is over. At 2 if I want, I have managed it. Now I want to find at 3 3, let us say. Stand here, either I can look down or I can look left. Okay, but if I stand here and look down, then what will happen? You see here, this is not looking like a cantilever. So make one more cut. Now this plus shape is looking like a cantilever. Because everywhere cut here, throw this piece out, is like a cantilever. Cut here, throw this piece out, cantilever. This is a cantilever because hinge you throw it out, VB, HB you show because these reactions are known to us now. So it's like a cantilever. Like this, even same way something here also. At 4 4 you want say. You have to cut here. Cut here at 4 4, see one side it is done. That means if you have, how many unknowns are there now? At each, how many closed cells are there you see? This is open cell, closed one is this, 1, 2, 3. 3 closed cells are there, you have to cut them, break the closed cells open. at each cut 3 reactions are there. So 3 into 3, 9 unknown reactions are there which you cannot find using equations of equilibrium. You may have to use compatibility conditions or some other internal joint equilibrium equations, find them, then completely analyze. Okay. So it is now like this. DSI means is calculated this way. 3 into number of cuts necessary, 3 into number of cuts necessary to open rigid closed cells. Closed cells or closed loops, any word we can use it. Then what is this 3 here? Axial force, shear force and bending moment at each cut. Now number of cuts means you can take it as a C. So DSI is nothing but 3 into C. In our case, number of cuts are required are 3. C is now in this case 3. So DSI you will get 3 into 3, 9 degrees. Like this. Now you see, this is only part information. Support reactions also are not known to us. We don't know them. But when you are finding DSI alone, DSE is known to us and your DSI is alone is 9. That means it is useless information because support reactions also you have to find anyhow. How many you cannot find? DSE. But still we found this one because there are certain cases where there are no supports at all. Only internal indeterminacy will be there. For such cases, we should know how to find the internal indeterminacy. For example, DSI for Ashok Chakra. Ashok Chakra we have known that there are no supports at all, only it is a wheel. Like this, total number of closed cells are some more I can show. 24 closed cells are there. This one closed cell, closed, closed, like that. It simply is a frame, not resting anywhere. So, such cases where there are no supports at all, DSI concept is useful. Okay. So, C means number of rigid closed cells must be there. All are rigid jointed ones. If it is not rigid jointed one, you have to make it rigid jointed. To make it rigid jointed, how many movements you added or how many reactions you added, you have to count. So many you have to subtract for the actual structure. We will see those cases. If hinges a rigid closed cell is not there, what to do? Make it rigid. Unnecessarily you made it rigid by adding some reactions. So many reactions you subtract if you want to use this formula. Okay. So, number of rigid closed cells or loops is 24. Now you see, DSI means 3 into C. C means number of cuts necessary to open rigid closed cells. Now number of cuts necessary naturally 24 because see here, this is one closed cell, I make a cut here. I make a cut here say, like this I have to make 24 loops are there, 24 cuts I will make it. Now you see, if I want to find axial force, shear force, bending moment at any section, supposing say it is 1, 1, stand there, look one side. If I stand here, look this side, this type of frame, I will get a cantilever frame. I made a cut here, this is 1 1. So this is like a cantilevering portion because there is a cut here. So this is cantilever. So wherever you want, you can stand there, look one side. That looks like a cantilever. So 24 loops, 24 cuts. So DSI means 3 into 24. You will get around 72 degrees. DSI for Ashok, DSI only will exist. Total static indeterminacy also same 72 because there are no supports. Okay. So such cases we require only internal indeterminacy. These cases internal indeterminacy alone not so much useful because reactions also are there which we don't know. But internal indeterminacy means only 9. Then external indeterminacy I calculated it as 3, 5, 6, 8 means 8 minus 3, 5. So external indeterminacy is 5, internal is 9. 9 plus 5, 14 is the total. So instead of calculating separately external and internal indeterminacy and adding and wasting the time, total static indeterminacy can be found directly. Let us see now that part, how to calculate total static indeterminacy for the beams, trusses, frames. Next, third one. Static indeterminacy. ds is equal to dse plus dsi. Without calculating dse and dsi separately, now we don't want to calculate separately and add them and waste the time. Now first we will take up the beams. For beams, ds is equal to dse plus dsi. This dsi is equal to 0 for beams. So I can write dse is nothing but r minus ds is equal to dse itself r minus s. When you are writing like this r minus s, if at all there are internal hinges also, let us say there are there, then in S you have to include those internal hinges, additional joint equilibrium equations also. That means internal equilibrium equations also included here. S is sigma x0, sigma y0, sigma m0. If at all there is any internal hinge, then bend moment is 0 in those locations. That is internal equilibrium equation that you add here. We will see in the numericals how we have to manage. But DSE stands for R minus S. That means for beams, static indeterminacy or external indeterminacy both mean the same. Okay, we know how we have calculated. Case 2 is for trusses. for trusses. For trusses, ds means total number of unknowns minus total number of equilibrium equations available. Total number of equations of equilibrium available. Now, you see here ds when you write, total number of unknowns are number of members, m members are there, say. So many unknowns are there. Suppose reactions are also unknowns. So m plus r. These are total number of unknowns. Minus total number of equilibrium equations available, external plus internal put together is 2j. So m plus r minus 2j. This is your static indeterminacy. Why we are writing 2j? Is suppose 10 joints are there, say. Each joint equilibrium I can take it. Sigma x0, sigma y0 I can use. Sigma m0 is useless. So, in method of joints, I have given you draw free body diagram of each joint. Two independent equations of equilibrium are available. So, in that truss structure, 2 into j number of equations of equilibrium you can list out for the total number of unknowns. M plus R put together. Okay. So, here 2j because at each joint we have two equations of equilibrium. Two equations of equilibrium, that is sigma x0, sigma y0. When you are splitting the entire truss into, separating into joints, then at each joint sigma m0 we cannot use it. So overall sigma m is equal to 0 we cannot use. But if you don't cut them, you may get sigma x0, sigma y0, sigma m0. But that sigma m0 extra we cannot add here because you have cut them into parts. Then each joint equilibrium when you are taking only this much. But without cutting sigma m also is 0, but that will be automatically included in this 2j itself. Okay. So, one of the equilibrium equation will match with the sigma m is equal to 0 will match with any one joint equilibrium equation. Okay. So, that is why total number of equations of equilibrium are only 2j. No sigma m is equal to 0 is applicable because at each joint when you take free body diagram, that means entire structure you split into two parts. Each pin joint, two equations of equilibrium including the support. Support also there is a pin. So, VA, HA and two member forces are there, say. There also you can use two equations of equilibrium only. So, in the two equations of equilibrium, supports also will come. And means support unknowns also will come. That is why total number of unknowns are m plus r. Okay. Now, let us see. One question will take total static in ds means static indeterminacy. Now you see in this case same question will take it. Generally we build simply supported trusses only. If nothing is mentioned, simply supported truss only. For the sake of adding one more, that means external indeterminacy also, one more support I have added. Okay. Now we see total number of unknown reactions are 4, VA, HA, VB, VC. How many members are there? Number of members are 11, number of joints are 6, support reactions are 4. So, ds is equal to m plus r minus 2j. Number of members are 11, reactions are 4, minus 2 into 6. 15 minus 12, 3 degrees. When we are calculating ds as 3 degrees, we do not know how much out of this is internal, how much of that is external. But since we have calculated separately this problem, then we can write it two internal, one external. But from this 3 degrees, we cannot tell how many is internal, how many is external. Some directly you will get. As you have calculated for this one external indeterminacy separately, internal indeterminacy separately, we found that one external and two internal. Internal indeterminacy was 2, external indeterminacy was 1, sum is 3. That sum directly we will get if you write m plus r minus 2j. In the exam, they will not ask you external separately or internal separately. Some they ask what is the static indeterminacy. So, this much is 2 minutes. A 2 marks questions. Here we can save your time. Maybe 10 seconds, 15 seconds it will take to complete the problem. Whatever time you save it, you can use it in MDM problem or SDM, slope deflection method problem, or if at all matrix method problem is given. Sometimes they may take 1.5 minutes, say, then 2.5 minutes also it will take, because you must get the idea. I will explain all the concepts, but which concept you have to pluck it quickly, thorough revision is required. So that's why there we can compensate. You may think some more time leisurely if you can save time here. So this is about the static indeterminacy for the trusses. Total static indeterminacy without calculating separately. Now we calculate it for frames. Now in this case, static indeterminacy became 3. Earlier it was 1. Sometimes if static indeterminacy works out to be negative, static indeterminacy negative means number of unknown reactions minus equations of equilibrium. If more equations of equilibrium available than the restraints, then it will become unstable. Example is, note you can take here. If ds is negative, then it means that the structure is unstable. Under what circumstances ds becomes negative is more equations of equilibrium than the reactions. Equations, if there is a reaction corresponding to each equation of equilibrium, then it is just stable. More reactions are there and it becomes indeterminate. Less reactions are there, it becomes unstable. Supposing that I give you this example. We have a beam like this, say A, B, C. Okay. Now, how many reactions are there here? VA, HA, here VB. This is floating hinge. Internal floating hinge. We have provided that one, say. Now, number of unknown reactions are 3. VA, HA, VB. That means sufficient. These are number of reactions, means they are like restraints. So 3 restraints are there. To find them, 3 equations of equilibrium are enough. S is equal to total number of equilibrium equations available. There are 4 available. What are they? Sigma x0, sigma y0, sigma m0. These 3 are called external equilibrium equations. But because of the hinge at C, bending moment at C is also 0. This is called internal equilibrium equation. So 4 are there. 3 external, 1 internal equilibrium equation is there. So S becomes 4. So ds is equal to R minus S. 3 minus 4 is equal to minus 1. Negative sign implies that the structure is unstable. Unstable means what? This again stability I will discuss. Rigid body translation or rigid body rotation takes place. That means on this structure, even if you don't apply any load, just tap like this, it will deflect. Large deflections will happen without developing any stresses. So unstable means this one. Structure is unstable or mechanism. Any which word we can use. That means this is a mechanism, because just tap like this, it will simply go down, that's all. To facilitate this downward movement, it goes left side. So this is called rigid body rotation. Rigid body rotation or rigid body translation. That means without developing any stress, it translates or rotates. That means it is unstable or mechanism. That will happen if ds is minus 1. That means one reaction is missing. Because of that, as a rigid body, it will rotate. Corresponding to equations of equilibrium, sufficient restraints must be there, so that only it will be stable. Otherwise, it will become unstable. Okay. So this is how the stresses ds we have calculated. Now let us see how to calculate ds for frames. Case 3. ds for frames. Now for the frames, there are many methods available. Textbooks will give you many methods, infinite loop or loop methods, etc. But out of all those methods that you find in the textbook with the formulas, I feel that the cantilever method of analysis is the most simple one, which with that you can complete any question that they give you within 30 seconds time. A 2 marks question can be completed in less than 2 minutes time. Maybe 30 seconds you can complete. Let us see what is that cantilever method. You have a multi-storied frame, let us say. Then what we do is, if you open only the closed loops, number of 3 into C, I have given you formula. C means number of cuts necessary to open closed cells. That's all. Just open the closed cell, you will get internal indeterminacy. Now we don't want open closed cells, completely separate the structure. For each support, you make a cantilever frame. Then to make a cantilever frame, how many cuts are required? So many cuts into 3, because at each cut you have sigma x, you have axial force, shear force, bending moment. So many reactions are unknowns which you cannot find at each cut. But about the support reactions you can find by using 3 equations of equilibrium: sigma x0, sigma y0, sigma m0. So, three equations of equilibrium are exhausted in finding the cantilever support reactions. Now, the cuts, right, at each cut three unknowns are there, so much you cannot find. So, that way, supposing that if you don't have a cantilever frame, make it cantilever by adding some reactions. 10 reactions you added to make it as a rigid cantilever frame, rigid jointed cantilever frame. Why rigid jointed? Only that is stable. Otherwise, cantilever in between pins are there, so then they will rotate. Unstable structures. For unstable structures, we don't find DS at all, dk at all. What is the use of that? One structure collapsed, let us say, then dk is 27 or ds is 34, no use, like that. So, we will make the cantilever method. We take the cantilever method, cut the frame. If in a frame 4 supports are there, say, then cut the frame such that you will get 4 independent stable cantilever frames. Then ds is equal to 3 into number of cuts necessary to make stable cantilever frames. Cantilever frame is total, you have to cut and separate them, not opening only closed cell. If you open closed cells only, first support to the second support also you can travel. Now the question of traveling from first support to second support should not happen, because you must break them. How many cuts? So many cuts into 3. So we will write that note. Cut the frame such that each part of the frame looks like a stable cantilever frame. Then ds is given by ds is equal to 3 into number of cuts necessary to make stable cantilever frames. This number of cuts necessary you take as a C. So ds becomes 3 into C. 3 stands for axial force, shear force and bending moment at each cut. So 3 quantities are there, so 3. Now let us see how to cut the frame so that we get independent cantilever frames, stable cantilever frames. Find ds. First we'll take the simple case. This is the frame, let us say A, B, C, D. So how many supports are there? 4 supports. Number of supports are 4. So we should get 4 cantilever frames. Now for 4 cantilever frames means first frame is here, make a cut here and here. Not only close cell opening, completely break it open. Here also break it open. Break it open. C means number of cuts necessary to make stable cantilever frames. How many cuts? 1, 2, 3, 4, 5, 6 cuts are necessary. Now you see 3 into 6 ds is equal to, now 3 into c, 3 into 6, you will get 18 degrees. This is sum of, it is the sum of DSE and DSI. Directly the sum you will get. Now what happens here is, this is a cantilever frame. You make a cut like this. Now after cutting it, it looks like this. First frame. Second frame, it looks now a stable cantilever frame is this one. First, after cutting it, separate it. Cut this one, plug this out. It looks now like this. Cut here, plug this also out. Now this frame now looks like this. Then fourth frame like this. Now each frame is a stable cantilever frame, A, B, C, D, let us say. Stable cantilever frame means, cantilever means not necessarily one member. Ends must, it's like a cantilever tree. In a tree, from one point to other point if you go, without coming from the same point, another end you cannot reach. So it's like that. No loop should be there. You go here, that's all. Again, if you want to go here, you should have to come back. From here, a circular loop you cannot make it. So it's like a cantilever tree. This is also cantilever tree. All ends are free ends. No looping is there. Such cantilever frames means, stable cantilever means what? This frame, hold here, pull it, leave it. Then it will vibrate, comes back to its original position. It should come back to its original position. No part, if you tap it like this, if it falls down, say, then it is not stable. So stable cantilever frame means, if you pull them and leave it, it should vibrate, should come back to its original position. So you have 4 cantilever frames. Okay. So total number of static indeterminacy is 18 degrees. Only internal, if you want to calculate, say 3 closed loops are there. So only 3 cuts are enough for internal indeterminacy. So 3 into 3, 9 degrees. External indeterminacy is 3, 6, 9, 12 support reactions. So R minus S, 12 minus 3 is 9. So external indeterminacy is 9, internal indeterminacy is 9. 9 plus 9, 18. That sum directly will get such cases. Now all of them are already rigid jointed cantilever frames. If they are not rigid, you have to make them rigid. Unnecessarily you are making them rigid by adding some reactions. So many reactions you have to subtract. Let us see what it means. Next question. Find ds. Now in the second problem, what we do is, instead of keeping B here, I will make a hinge here. Here I will keep a roller support. Here I will keep a guided roller support. This is your actual structure, say. Now, number of supports 4, so 4 cantilevers, this is okay. Number of cuts necessary to make stable cantilever frames, this is also 6. Okay. This will write again. C is equal to 6. Number of cuts necessary to make stable cantilever frames. Now if you cut them and see, first frame is like this. Second one, B is not a fixed one. You see here there is a hinge. Here there is a roller. Here there is a guided roller. So your four cantilever frames are like this, but they are not stable. First frame, you see, this problem after cutting it, number of cuts are 6 only. Pull it like this and leave it, it will come back to its original position. For any structure, any plane structure to be in stable condition, 3 reactions are required. Minimum 3 must be there. Why only 3? Because you have 3 equations of equilibrium. Corresponding to 3 equations of equilibrium, 3 restraints must be there. Otherwise, it will become unstable. That means, supposing that sigma, you have a structure, let us say, 10 forces are acting from right to left, say. At least one restraint or one horizontal reaction must be there from left to right to make sigma x is equal to 0 to happen. So, for sigma x is equal to 0, one restraint is a must, one reaction is a must. 10 forces are acting vertically down. At least one reaction in the form of a force must act from upwards. So, if 10 are acting downward, at least one must be upward to make sigma y 0 to happen. So, to make sigma y 0 to happen, one restraint must be there, which will produce one vertical reaction. Okay. Then, on a structure, 10 clockwise moments are there, say. At least one anti-clockwise moment must exist to make sigma m 0. So, 3 equations of equilibrium, 3 restraints must be there. If any additional equation of equilibrium available, corresponding to that, one restraint must be there. If not there, it will become unstable. That's why ds becomes negative, it will collapse. So, how many equations of equilibrium? So many restraints must be there to hold the structure. So, in this case, it is stable because 3 reactions are there, but it is not stable. Why it is not stable? There are only 2 reactions, one vertical horizontal moment reaction is missing. So, what happens if you tap it like this, it will rotate and fall down. For that moment, sigma m is equal to 0, you cannot make it because this cannot give any moment reaction to make sigma m 0. Okay. So, 10 clockwise moments are there, no anti-clockwise moment, so it will rotate and fall down. So, since it is not stable, because of the, why it is not stable, insufficient number of reactions. So, what we have to do? You fix it. Unnecessarily you fixed it by adding how many reactions? Already 2 existing reactions are there, VB, HB, MB is missing, by fixing you added, but unnecessarily you added, you subtract, minus 1. Now, it is a stable cantilever. Now, for making stable, you added one reaction extra, then subtract. Then why should I unnecessarily add and subtract? I want to use that 3 into C formula. 3 into C formula is valid for stable, rigid cantilever frames. If any structure is not rigid stable one, make them rigid stable. Then for that, how many you added, subtract, then I can use happily that formula. That's why we added, subtracted. See here, roller is there. When you tap it like this, it translates and falls down because only one reaction is there. So, vertically only it cannot move because vertically you stopped. Sigma y0 you can make it. Sigma x0, sigma m0 not possible because the restraints are not there. So, as a rigid body it will translate. So, fix it. Unnecessarily fixed by adding 2 reactions. So, subtract 2. Here only 2 reactions are there. VD, that means vertically it cannot move. MD, that means it cannot rotate. But rollers are there, sigma x, horizontal reaction it cannot give. So, if you tap it like this, restraint is not there. So, as a rigid body it will translate. So, fix it. By fixing it, you added one reaction. So, subtract 1. Now, you see you have 4 stable cantilever frames. To get them, you unnecessarily added 4 reactions, so much you subtract. So, your DS is like this. Static indeterminacy is formula is 3 into C minus number of reactions unnecessarily added to make stable cantilever frames. So, ds you will get 3 into 6 18 minus 1 at B minus 2 at C minus 1 at D. So, you will get 18 minus 4 14 degrees. 14 degrees is for the actual structure. Why minus 2 you add, write a note. Minus 2 because to make roller support as a fixed support, we unnecessarily added 2 reactions. So, subtract 2 from ds. That is the reason. In case at later stages you get a doubt how minus 2, to read that minus 2, this is that. First fix it, 2 reactions added, then remove it. So, minus 2 subtracted, then you will get ds for the actual structure, not for the rigid jointed frame. It is not a rigid jointed one, hinge, roller, guided roller. But if I use 3 into C, I will get all rigid jointed structure. If they are not rigid jointed, so many reactions unnecessarily were there, you subtract them. You will get the actual ds. Now, we will take one more problem. This I remove. This also now not required. Now you see third problem. This is now third problem. Find ds. Already now is there. You add one more hinge here. This is D. Let us say E. This point say F. These are internal hinges at D, E, F. Internal hinges at D, E, F. Now for this structure we want to calculate. Now already I have given you number of cuts are how much? See, in this case number of cuts is 6 again. Same problem we have taken here. Minus 1, minus 2, minus 1. This point you understood. Now let us see D. At D, after cutting it, how it looks like is this way. The structural behavior at D is like this. This is one member and pin connection is there, means there will be one gusset plate to accommodate the connections of all the members. So, there is a pin here. After cutting it, the second member is like this. Third member is like this. Like this is point at D, joint at D. A, B, C, D. Okay, we change the notations. Instead of that, already D, F you have written. You make A, B, C here say. Then this becomes D. Instead of rewriting all that. So, D. D joint I have shown here. Okay. Now, after cutting here, like this, when you cut it, this comes now like this. You are cutting it here. It must look like a stable cantilever frame. Is it a stable cantilever? After cutting here, see, hold this and you can lift up and down, or if you pull it like this or push it down, it will fall down. It is not a rigid jointed one. Here fine, it's okay. This is also same thing. This L-shaped member I can rotate easily. So first, if I want to use 3 into C formula, you must have all rigid jointed cantilever frames. If they are not rigid jointed, if they are pin jointed, first make them rigid jointed. Then you can use the formula happily. So to fix this one, it is rotating. So you have to add one moment here. This is a gusset plate, you can take it. Steel structures also will get this gusset plate, which accommodates connections of all members meeting at a joint. Gusset plate means a plate which accommodates connections of all members meeting at a joint. So one such gusset plate we have used. Actually, if you see from far off, you cannot see the gusset plate. Simply pin, you can see. If you go nearer to that, you can see a plate like that. Sometimes they can overlap and long pin they can insert it. Then we cannot feel the structure DS clearly. So I have separated like that. Okay. So this will rotate. Stop that rotation. Assume that you have applied one moment, say 10 kilonewton meter. Some value, unknown value. It is actually rotating anti-clockwise. You fixed it by applying some unknown moment, some MA, some 10 let us say. Then this one is rotating, say, anti-clockwise. You apply, it's rotating this way, fix it. Unnecessarily you are fixing here. Say you apply 20. Then here, for the gusset plate to be in equilibrium, this moment cannot be independent. It has to be 30 only. If 2 are clockwise, this has to be 30 kilonewton meter. It is not unknown. Why? From sigma md is equal to 0. Moments of all force about D. Internal moment at D must be 0. Sigma md is equal to 0 at joint D. This is internal joint equilibrium. This plus this must be 0. So this is not unknown. Only 2 unknown moments only you added. Third moment you didn't add. That is automatically existing. That is known to us already. So since you added 2 unknown moment reactions, we didn't add 3 unknown moments. See, only here if 3 are there, so if this is 20, this is 30, this is 70, we don't add. If you add 20, 30, 50, then this has to be minus 50 only. That is not an unknown quantity. Because from sigma m is equal to 0 of the joint also must be satisfied. So you added 2 unknown moment reactions. Now it became a rigid jointed one. So to make D as a rigid joint, we have unnecessarily added 2 moment reactions. So subtract 2 from ds. Only you have to subtract 2 from ds. So minus 1, minus 2, minus 1. If 3 members are there, you have to subtract only 2. Third one is known to us. At this point, there are 4 members. Unknown moment reactions you have to add only 3. Fourth one is known to us. Since you added unnecessarily 3 reactions, subtract, because you want to get ds for the actual structure, not the rigid jointed one. Here 2 members are there, so you have to add only unnecessary moment reaction only one. That means if you apply here plus 10 say, it cannot be minus 20. If it is plus 10, it has no choice. How much it should be? Minus 10. So this is minus 10 plus 10 means only one unknown. Sum must be 0. So only one you have added. So now ds is equal to static indeterminacy, ds is equal to 3 into c minus number of reactions unnecessarily added to make stable cantilever frames. So number of cuts are 6, 3 into 6 minus 1 reaction you added at A to make stable cantilever, 2 at B, 1 at C, minus 2 at D to make stable cantilever, 2 reactions you added at D. You added 3 at E. You added 1 at F. Whatever you added, you subtracted. So actual structure will get ds. So 3 plus 1, 4, 6, 10. 18 minus 10, 80 degrees. So static indeterminacy is 8 degrees. Now let us see one more question. This joint pins need not be kept at the joint only. You can keep the joint next to the rigid joint also. Then let us see how it behaves. Now fourth question, find ds. Now this is pin kept at the joint itself here like this. This point let us say A, this point let us say B. You should not think that by mistake this circle is supposed to be kept here, by mistake they kept it here. It's not by mistake, it is intentional. This is a pin next to the rigid joint, this pin at the joint. This is pin next to rigid joint. This is pin at the joint. Structural behavior is totally different. Now let us see how many cuts are required. 2 supports. Number of supports are 2. So 2 cantilevers. Okay. Next, number of cuts required also 2. C is equal to 2. Next, at A. Now this is a point A. This same diagram I will make use. To make A as a rigid joint, we have unnecessarily added 2 moment reactions. So subtract 2 from ds. So this is same as this one, minus 2. 3 members are there too, but this behavior is different. Let us see how it looks like. this is now we can write A, no, sigma m A is equal to 0 at joint A. Okay, that A is similar. Now how B looks like? B next to the rigid joint means it is like this. This is the column. This is one member. Okay. Now at this point you may have to provide one plate, let us say a plate is welded. To this one we added one more member like this. This is B. Pin next to the rigid joint. Pin at the joint means if this is connected like this, separate members are there, say. Here 3 separate members are pinned. Here from ground floor to the top floor only one member. So this member, when I pull it and leave it, this completely vibrates and stops. Whereas here it is not the case. This independent of this I can move it. Okay. Now only one moment. If I apply, say, this freely rotates. To stop that rotation, if I apply plus 10, then on this minus 10 will be there. That is known to us. So only one moment I have to add. So to make B as a rigid joint, we have to add one moment reaction only. So subtract 1 from ds. Now your ds is like this. I can write here. Now ds is 3 into C minus number of reactions unnecessarily added to make stable cantilevers. So 3 into 2, number of cuts are 2 only, minus 2 at A, minus 1 at B. So much difference is there, so much structural behavior difference. Hinge at the joint, hinge next to the joint, both structurally meaning different. This will write 6 minus 3, 3 degrees. Sometimes instead of giving this and this also identical, you see here, this is the frame, let us say, this or this. This is coming. This member you can overlap it like this also. Like this. Or in other words, I draw a bigger one. Fix it here. This is one member. This one you can take a plate, weld it. To the plate you put a pin and connect it. If this arrangement is not there, this is also same. I pin it here, say. Now you see this vertical member to this one is a single one. When I pull it and leave it, it will vibrate and stops. Only this one rotates. Fix it by applying plus 10 on the member. Then here minus 10 will be there. So moment you added only one. Other one is not unknown. It's same thing only should be there. Sigma m has to be 0. So this is also B. This or this are identical. Or this way. There are 3 ways of representing the same thing. overlap and bolt it, or weld a rigid plate and pin it, or show a line diagram like this. All diagrams mean identical. This means at the joint itself circle is provided, it is like this. Okay. So, if you know the structural connections, how they are connected, how they are represented, actual behavior if you understand, then answering becomes simple. You don't have to by heart how many reactions we have to add to make rigid cantilever frame. Okay. Next one. Supposing that this I remove, now let us see one more question. Find ds. If this is the portal frame, you can take it. If the beam is too long, let us say, then when loads are applied, excessive deflections will happen. Such cases, what we do is you brace them by adding members like this. Here also like this, so that these will act as a stiffeners or bracing members like this. So, these are called knee braces. Knee bracing used to reduce bending moment and deflection in beams. Okay. This way, this if they want to show as a line diagram, they will show it like this, or this way. Both diagrams mean the same. Like this way. So, you must understand that they are knee braces, okay, they are pin connected. Now, this and this are same. How many supports are there? Number of supports are 2. So, 2 cantilevers only. We must get 2 cantilevers only. To get 2 separate cantilevers, how many cuts are required? If you cut here, say, 1 cut here or 1 cut here. If you make only 1 cut, then what will happen? It is not a cantilever. There is a closed loop here, loop here. You must cut the frame such that there should not be any closed loop in any part of the structure, and no part of the structure should fall on the ground. Supposing that means if you cut here, 1 is enough, 1, 2, 3, 24, 26, 57, 58, like that you cut, say 58 cuts also you can make it, then entire structure will fall on the ground. You will have only one small piece here. That way we should not cut. Cut the members such that, cut the frame such that no part should fall on the ground. No closed loop should be there. So, to avoid the closed loop here, you break it open. Here also break it open. So, 3 cuts are required. Here also 3 cuts. So this is the first requirement. So this is the condition. We'll write note here itself. This is sometimes knee bracing purpose they can ask you as a 2 marks question. This is the note. Cut the frame such that there are no closed loops and no part of the structure falls on the ground. So from this you require 3 cuts. So number of cuts are 3. Okay. Now after cutting it, now is this point you take say A, B, C, D. Here also this is A, B, C, D. It must be a rigid jointed one. 1, 2, 3 cuts you have made it. This frame, what will happen after cutting it? This will rotate. At this pin location, this member rotates. So fix it. Unnecessarily you are fixing it, you subtract. Already 2 reactions will exist, only rotation freely it will rotate. So to fix it, you have to apply 1 reaction. Since you applied 1 moment unnecessarily, you subtract 1 here. Same is the case here. This member will rotate like this. So we should, that means as a rigid body it will rotate. So fix it. Unnecessarily you are fixing it, so subtract. So is the case here. Unnecessarily fix it, subtract 1, 1 here. So is the case here also. Minus 1, minus 1, minus 1, minus 1. 1 moment you added to make it as a rigid joint. Since you unnecessarily added, you subtracted 1, 1, 1, 1 here. 4 places you have to make them rigid. So 4 reactions you have to subtract. So now your ds is 3 into C minus number of reactions unnecessarily added to make stable cantilevers. So 3 into 3, 9, minus 1 at A, minus 1 at B, minus 1 at C, minus 1 at D. So 9 minus 4, 5 degrees. In one of the ESC prelims they asked this question. Any question they ask you, you can manage with this concept. You should understand these points. How we should cut the frame to make them rigid, how many reactions we have to add. When they show you the internal pin in a framed structure, how the connection is made, if you have clarity, then you will know how to fix it, how many moments are required to fix it, then so many you can easily subtract confidently. Otherwise, if that pin looks like a black box, say we don't know how it is connected, some value will write to subtract it, then you are not sure whether what you have done is correct or wrong. That problems will come. Next one. Next question we'll take. For the bowstring girder shown in figure. Find ds. Bowstring girder means they are like a beam constructed in the form of a bow. Line diagram I have shown. It is a beam girder means beam, a simply supported beam. If you have a simply supported solid beam, then depth, let us say 3 meters or 4 meters, sometimes 5 meters depth of the beam, not possible. Due to self weight itself it will fail. So what we do is, instead of having a solid beam, a beam made up of holes. So bottom flange, top flange, bottom flange are connected by webs, that's all. If you see the London bridges type things, this type of bridges you see in the olden days for small spans, maybe around 15 meters span, like that, as they say. This is like a small river is flowing, you assume. Two pairs here, another two pairs at a distance of 10 meters, one more bowstring. Between the two bowstring there is a deck. We enter the bridge, we leave the bridge. Such bridges, single beam if you provide, it will be too costly. Means depth of the beam, money, lot of money is wasted. So what we do is, a beam in this shape, bowstring girder in the shape of bowstring. So this is like a bow. This depth will be 5 meters and one hangers will be there. Here everywhere gaps only will be there. So that moment of inertia, bending moment, it can take very effectively. Moment of inertia will be very high because the distance between top flange and bottom flange runs in terms of meters. Like a truss, top flange, bottom flange runs into 4 meters, 5 meters. So that is a truss. But it is a rigid joint. Truss means pin jointed, it is a rigid jointed one. We call it as bowstring girder, or sometimes Verendel truss also we call it. So such cases, if at all shear is acting, let us say shear force. So shear force, there is no solid web. I told you in the moment distribution method that the shear deformation is neglected in the analysis of MDM, slope deflection method, and you can neglect if you have a solid web. Now no solid web at all, bottom one line, top a curve, only lines. That web is everywhere, holes only are there. Such cases, shear deformation also must come into picture. You have to design the members for shear deformation also. So this is a bowstring shown in figure. Find ds. All joints are rigid. A concrete structure or something like that, let us say. See, all joints are rigid. Now let us see how they have given a pin here, roller here, and it is a rigid jointed. A rigid jointed structure kept on a hinge support and roller support. How it is kept? Like this is, if you see, go nearer to A, rigid jointed structure means like this. We have a gusset plate, like this will be there, and there is one curved member running, one horizontal member. This is one horizontal member, say. This is a curved member, and it is rigid jointed means maybe it is welded, like this. This entire construction is kept on a pin hinge support, like this. There is a pin here. A rigid jointed structure kept supported on a pin hinge support means like this. Rigid jointed structure kept on a hinge support. maybe there are this type of triangular plates, two will be there, one front side, one back side. Your pin must go from here to the back side also, and this entire truss rests on that such a thick pin. Okay, it goes in. Now you see, this is the meaning of that. If I hold the black color, this member, hold it and lift it, say, this plus this gusset plate it is. I think I have already given the diagram. Entire thing rotates as a single unit, but I want to make it as a fixed one cantilever. So fix it. To fix this one, you require only one moment reaction, because already two reactions are there. To make A as a fixed support, we have to add one reaction only. What is that? Moment reaction only. We have to add one, say, moment reaction only. So subtract 1 from ds. So here it is -1. Now let us see. You must cut the two cantilevers only should be there, because two supports, two cantilevers. Two supports, so two cantilevers. No part should fall on the ground, no closed loop should be there. 1, 2, 3, 4, 5 closed loops are there. You must cut such that no closed loop. So when I am fixing it here, I can cut like this. If I cut like this, and I can hold it and take it out, and this portion I can hold it, again this I can take it out. So I will cut it, say, like this. Like this. Now you see, there is no closed loop at all. Here the entire thing is like a cantilever. This is also like a cantilever. How many cuts are there? 1, 2, 3, 4, 5, 6 cuts are there. Any one cut extra if you make it, say, so one cut you make here, this is separated, this part will fall on the ground. Supposing that this idea you are not getting, cut it vertically. 1, 2. 2 cuts separated. Now 2 closed loops are there. 3, 4 you can make it. 5, 6 you can make it. 2 vertical, 2 here, 2 here. Then also cantilever only. Whatever idea you get it, but don't cut them complicatedly, so that whether closed loop is there or not, if we don't have clarity, difficult. Cut a single one line like this, so that it should be separated, no closed loop. Okay, complicated cutting, if you make it, counting itself will become difficult. We may miss some closed loop itself. Whether closed loop still, whether we have broken it open or not, also we will get doubt. So number of cuts required are 6. Okay. Now this is over. How A looks like: a rigid jointed structure kept on a pin. Here this a rigid joint, all joints are rigid, a rigid jointed structure kept on a roller. How B looks like is this way. Rigid jointed means maybe it is welded, or too many bolts are there, so that it behaving like a rigid jointed one. It is not free to rotate. You have welded here. Now this is a single unit. Now this is kept on a roller, means like this. A pin here, guided roller here. This is B. This is the roller support, we call it, because it rolls as well as rotates. If it is rigid jointed one here, pin is not there, then it becomes like, we call it as a guided roller support, Between guided roller support, simply roller support is that pin extra. That's all. Okay. Now you see this black color one, if I hold it and lift it, it will rotate here. So I have to fix it by adding one moment reaction here. But here you see, after fixing it, this will slide. That horizontal also you have to stop it. So I will fix it here also. So to make B as a fixed support, I have to add two reactions, one moment reaction here, one horizontal reaction here, then it behaves like a fixed support. Since you unnecessarily added two reactions, subtract 2 from ds. So this is rigid jointed one, means like this. If it is pin jointed, they give you, say, then bolts you have to provide. Then this and this independently they will rotate, number will be different. To make B as a fixed support, we have to add one horizontal reaction and one moment reaction. So subtract 2 from ds. Now your ds becomes like this, 3 into C minus number of cuts are 6 minus 1 at A minus 2 at B. So that means 3 into number of cuts are 6 minus 1 minus 2, 18 minus 3, 15 degrees. So static indeterminacy is 15 degrees. Okay. So this type of one gate paper, if you see the old papers, 2 questions on this one given. All joints are rigid means first you see rigidly you connect it, then put a hinge there. Rigid connected, put a hinge. Then you will know how to fix this one. How many reactions are to be added. Okay. Then accordingly you answer that question. No formulas are required. This much is sufficient. This looks, to draw the diagram looks time taking, because I am assuming that you are learning for the first time how a rigid jointed structure kept on a hinge, how a rigid joint is kept on a roller. That if you have the clarity, it takes here minus 2, minus 1, cut it. 30 seconds you can complete. Now one more question we will see on this. Find ds. Fix it here, fix it here. A hinge was there, something like that. This is how structure is there. This point, let us say A, B, C. This is called hybrid structures, part pin jointed, part rigid jointed. First, how many supports are there? You count 1, 2, 3, 4, 5 supports. So, number of supports. In the rough work, you don't have to explain this, all this nonsense. This story you don't write in the rough work. Number of supports are 5. So 5 cantilever frames. That is only for our understanding. Till you become familiar, we are writing. Number of supports are 5. So 5 cantilever frames we should get, or 5 cantilevers we should get. Now 5 cantilevers means this one support cut here. This is a cantilever beam separated. Second one support is here already separated. This if I want to separate, cut like this, this will come out. Now for this one to come out, cut here, here, here. This part will come out. Simple way of plucking it out. Then this one if I want to pluck it out, cut one more, it will come out. Now this is separated. No closed loops, no instability anywhere. How many cuts are there? 1, 2, 3, 4, 5, 6, 7, 8. So 8 cuts. Here at A, how many members are meeting? 1, 2, 3 members are meeting. It is a hinge, internal hinge. So to make it as a rigid jointed one, you have to add only 2 moment reactions. Third moment is known to us. If this is 10 plus 20, this has to be minus 30. So since you added 2 reactions unnecessarily, subtract minus 2. Here 1, 2, 3, 4, so minus 3. Here hinge support is there. How many moment reactions we have to add unnecessarily is, supposing that if I see the C point carefully, see that's why one point at the support I have given, it is not a rigid jointed structure kept on a pin. He didn't mention that all joints are rigid. So it is a pin support only. A rigid joint kept on a pin, not the case. Once they put a circle like that, a bolted connection only. That means if you go nearer to C, it looks like this. This is the pin gusset plate, let us say. Okay. This is one, this is the support. There is a bolt here. This is C. Now, since it is not a rigid jointed one, it is a pin jointed. So, one member like this, circle you put it. It is a pin jointed structure. The member is pin jointed to the gusset plate. If they say that it is a rigid joint, then weld it, as I have shown earlier diagram. This is also bolted. Like this. So at C, there are 4 pins. Supposing that this will freely rotate, assume that I fix it by using 10. This I will fix it by applying 20. This I will fix it by applying 30. 10, 20, 30, total 60. Now the fourth moment here, it is not unknown. Once you fix it, this has to be 10, 30, 30, 60, it has to be 60, not unknown. So to make C as a fixed support, I have to add 3 moment reactions. Fourth moment is not unknown. To make, be careful of at the support if they put bolt like this. If you go nearer, it looks like this. To make C as a fixed support, we have to add 3 moment reactions only. Fourth moment is not unknown. So subtract 3 from ds. So here you have to make minus 3. What care you have to? You see, 4 members are there, 3 is subtracted. 3 members are there, but still you subtracted 3 because fourth one is the support pin. Okay, like this. Now, if you find ds, 3 into C minus number of reactions unnecessarily added to make stable cantilevers. Okay, So 3 into number of cuts are 8 minus 28A minus 38B minus 38C. So 6, 8, 24 minus 8 means 16 degrees. Like that. So this is the complete information about the static indeterminacy for beams, trusses, frames. Cantilever method is the best way to get out of the problem quickly for any type of structure they give us. Okay, internal indeterminacy, external indeterminacy together, total static indeterminacy only they ask you in the exam. But some questions I have given you internal, external separately because as I have told you the Ashok Chakra type frame, no supports are there, only internal indeterminacy will exist. If you take beams, only external indeterminacy, no internal at all. Okay, so that's why we have first calculated separately, then calculated together. Next we will take the kinematic indeterminacy.